learning and why we need to study reinforcement learning. And so there is this uh, very nice tutorial by OpenAI. It's called spinningup.openai.com, and it's a very nice place to start with reinforcement learning or deep reinforcement learning. So we have already seen a lot of examples of deep learning, and today we will see what is reinforcement learning. So it's basically an area of machine learning concerned with how intelligent agents ought to take actions in an environment in order to maximize the notion of cumulative reward. Like that's the definition of Wikipedia. Well, let us go through some of the basic terminologies of reinforcement learning. What are the key concepts, and we'll see the language and the notations of the subject, and a very high level explanation of what these reinforcement learning algorithms, or what are known as the RL algorithms, what they can do, and little bit of the core math that underlines the algorithms. So for those of you who know, like, or for those of you who actually don't know, OpenAI is a leader in AI based research and products. One of like its initial founders was like Elon Musk was its founder, and they have OpenAI and DeepMind and others. They have been leading this revolution of uh, like deep reinforcement learning. So deep reinforcement learning is what basically led to, if you have heard of this Netflix series called AlphaGo. So AlphaGo is a program which defeated the world champion of Go. Go is a game like chess, and it has it. However, the board is bigger, and you have these the white and black pebbles. So there are some rules of this game, and this guy, he is the world champion of Go. So these are professional Go players, and this is a real documentary, and DeepMind trained this program to learn how to play this game of Go, and they made it learn with the world rank fourth or fifth guy, and then they kept a competition or a series of matches which was live streamed, and the press release used to be done before the match and after the match. And AlphaGo, which was the name of the deep reinforcement learning algorithm, it defeated the world champion of Go in 2016, and that was actually a big leap for mankind, that and a model which is artificial, it is trained, it can defeat the like it can outdo human intelligence, was something which was really awesome. So this was like why I am telling you this is just to give a motivation on what can deep reinforcement learning do. So deep reinforcement learning is heavily used in games, and in so there is this protein folding problem in biology. So yeah, so it says AlphaFold. So they call this program as AlphaFold, and a solution to 50-year-old grand challenge in biology. So protein folding is a challenge, and the previous state of the art algorithms, you can see their accuracy used to range from 20 to 40%. The original AlphaFold implementation was able to substantially increase the accuracy of the model, and AlphaFold 2, it has taken it beyond 80%. So these are the different structures of proteins. Now, deep reinforcement learning we have seen can be used in games for biology. It can also be used for if you are doing like finance. So people doing people basically working at the intersection of finance, sustainable finance. These days a lot of people are talking about climate finance. So you can make use of deep reinforcement learning for those applications. You can make trading bots, chatbots, or risk optimization. Optimization, like any kind of optimization that we do in our field, you can basically mimic an algorithm from that field to our field. And so these are the different applications in finance. There are applications. So there is a paper, okay, climate, yeah. So there was a near optimal deep reinforcement learning policies. So in 2018, this kind of there was this first paper by, so that guy is a student of Vedartha. I'll just, yeah, his name is Felix. Yeah, so Felix Strand Deep Reinforcement Learning. So Felix actually first proposed this thing. He wrote a paper in 2018 on how to basically make different strategies, sustainable management strategies for the future using world earth system models. So you have so what they did in this was basically they have an environment which is for example the earth system environment, and that environment, so the you are having an agent. So the agent in this case is a deep learning model. The agent is taking an action. So this is although a generalized framework of any deep reinforcement learning problem, but in this case also, so they have you take an action. So the actions can be that you are implementing carbon tax, or you're having subsidies for renewables, or you're having nature protection policies. So then after taking the action, the environment will give the next state. So for example, you reduce the carbon dioxide in the atmosphere, the environment will give you a response to that, right? It will give you the next state. It will give you, let's say, a less warm future, and it will be associated with a reward or with some kind of positive reward or negative reward. And so this is the framework that he used. Uh, it's it's the it's the reinforcement learning framework. And in reinforcement learning, if you if you replace your agent with the deep learning model, that basically becomes deep reinforcement learning. So we'll talk about what is q learning, what are deep q networks, what is experience replay. I'll just briefly show you what he was doing. So for example, you see this figure. Okay, so this one is so on this axis you have excess atmospheric carbon, the stock in gigaton carbon. On this axis you have the economic output, right? So in US dollar, 10 to the power 12 US dollar per year. And on this axis you have renewable knowledge stocks. So how much of renewables are we having? So we basically have to minimize the carbon in the atmosphere, maximize the economic output, and also that we can control with this renewable knowledge. So how much of renewable knowledge is there? And these are the different policies. So these we call as the different policies. So you can basically construct this kind of a 3D plot and see what is the policy which would lead to a sustainable future. So that is the underlying idea of this work that he did. And you can use deep reinforcement learning for like basically anything, like for it works better as a full framework. For example, you can use it for time series, right? So deep reinforcement learning for time series, you can you can pretty much apply it anywhere where you can use deep learning and see whether you are getting improvement from the existing agent or the algorithm as such, or using it as a standalone algorithm. And what can RL do? So RL methods have recently enjoyed a wide variety of success. For example, it's been used to catch computers to control robots in simulation. So this is an agent who is playing a game. Now, its aim is basically to hit the football and to get make a goal. But this agent is always is being hit by some kind of obstacle. So that is a constraint that is being put on this agent. Like that's how this problem is defined. So that is something you have to define in the environment. So in the key concepts and terminology, we basically have an environment. Now the environment gives a state and a reward to the agent. The agent takes an action, and this is known as the agent environment interaction loop. So the main characters of reinforcement learning are the agent and the environment. Agent environment is the world that the agent lives in and interacts with. So we all are agents who are living on this planet Earth, which is an environment. And at every step of interaction, the agent sees a possibly partial observation of the world. So just like we would see an observation of the world around us, the agent will see a partial observation of the state of the world and then decides on what action to take. So the agent will take an action based on the observations that it gets from the environment. And the environment changes when the agent acts on it, but may also change on its own. So there are different rules by which the environment will function, and based on the agent's actions, it would respond, maybe respond or maybe not, depending upon the environment. And so the agent perceives a reward signal from the environment, a number that tells it how good or bad the current world state is. And the goal of the agent is to maximize its cumulative reward called return. And so the reinforcement learning methods, just a second, I will close the door. Yeah. So the reinforcement learning methods are ways that the agent can learn behaviors to achieve its goal. And so to talk more specifically what RL does, so there are these further terminologies. Like we have already seen states and observations, action spaces, policies, trajectories. So what are the different formulations of return? the RL optimization problem, the value functions. So what is a state? State is a complete description of the state of the world, and there is no information about the world which is hidden from the state. So it contains of all the knowledge from the environment, which is a complete description of the world. And an observation O is a partial description of a state. So it's like you can think of as subsetting or bootstrapping some information from the state, which may omit, which may not be the complete information. And in deep reinforcement learning, we always represent states and observations by a real valued vector, matrix, or a higher order tensor. So just like we have seen how we would embed or create embedding in natural language processing, or in nonlinear time series analysis. So these states and observations will also be are also represented by real valued vector or matrix. And for instance, a visual observation could be represented by an RGB matrix of its pixel values. The state of the robot might be represented by its joint angles and velocities. So when the agent is able to observe the complete state of the environment, we say that the environment is fully observed. So when the state and the observation, they are the same thing. It's a fully observed environment. And when observation is a partial representation of the state, that's partially observed. And reinforcement learning notation sometimes put the symbol for state S in places where it would be technically more appropriate to write the symbol for observation. And specifically, this happens when talking about how the agent decides an action. We often signal in notation that the action is conditioned on the state, when in practice the action is conditioned on the observation because the agent does not have access to the state. So in practice, people would talk about what people would talk about as state is actually an observation. It's not the entire state, but that's just about the notation. And then we have something known as action spaces. So what are action spaces? It's a real valued vectors or continuous spaces. It's like a sequence of actions, right? Whether you have to go right, left, up, down. If let's say these are the four actions, so you just keep collecting a series of actions for that the agent has to take. That is known as the action space. So they say that the set of all valid actions in a given environment is often called the action space. And some environments like Atari and Go have discrete action spaces where a finite number of moves are available to the agent. So other environments like like where the agent controls a robot in a physical world have continuous action spaces. In continuous spaces, actions are real valued vectors. And so this distinction has quite profound consequences for methods in deep RL, and some families of algorithms can only be directly applied in one case and would have to be substantially reworked for other. So then comes the concept of policies. So policy is a rule used by an agent to decide what actions to take. So it is like a sequence of actions that the agent is trying to take. So you will have different policies, and you will have to choose a policy such that your your cumulative reward is maximized, right? And it can be deterministic, in which case it is denoted by mu, or it may be stochastic, basically is denoted by pi. So it can be it can have both these representation as deterministic or as stochastic. And because the policy is the agent's brain, it is not uncommon to substitute the word policy for agent. So people would use these two words, policies and policy and agent, as interchangeably. because policy is what is deciding what to do, which actions to take, and the policy is trying to maximize reward. So in deep RL, we deal with parameterized policies, policies whose outputs are computable functions that depend on a set of parameters. So that is the weights and biases of a neural network, which we can adjust to change the behavior via some optimization algorithm. So that's what we have. So that's what makes it deep RL, right, and separates it from the traditional RL. So basically, if you are using deep learning, and now what you have is what is known as the parameterized policy, so whose output are computational functions that depend on a set of parameters. So the output of the policy, right? So what is the policy giving you? It's giving you a set of functions. uh, so it's giving you the functions that are inherently dependent on some parameters, and those are basically the weights of the deep neural network. And we often denote the parameters of such a policy by theta or phi, and then write this as a subscript on the policy symbol to highlight this connection. So the policy will basically take state and it will output an action. This is the policy mu, or in stochastic sense, if you can see, you have the policy as pi. So let us see this example of a deterministic policy and this code. So this one is a policy. It's written in PyTorch. So you can see that this is a sequential neural network. So you have a linear layer first, and its input is so its output is what is the observed dimension. So it has got these two arguments: observed dimension, comma 64, 64, and so this is the input dimension, this is the output dimension, and then you have the nonlinear activation function. So again, linear combination, nonlinear activation, and then finally you will map from the observation dimension to the action space. So what is this policy doing? It is taking you from the states. It is taking in as input the states which are which are independent variables to the, and it is giving you the actions, right? And this builds a multi-layer perceptron network with two hidden layers of size 64 and tanh activation functions. If OBS is a NumPy array containing a batch of observations, PyNet can be used to obtain a batch of actions as follows. So let's say you have an observation tensor, you may define it as a PyTorch. So OBS is a NumPy array, and you transform it to a tensor. And then if you pass this OBS tensor to PyNet, so that gives you the set of actions. And okay, so I think you don't need to worry about this because this neural network stuff should be familiar to you by now. And stochastic policies. So the two most common kinds of stochastic policies in deep RL are categorical policies and diagonal Gaussian policies. So categorical policies can be used in discrete action spaces, while diagonal policies are used in continuous action spaces. So action spaces can be discrete or continuous. So by discrete we mean that for example, your integers are a set of discrete numbers, whereas real numbers, which can have all the decimals. So numbers from, let's say, 0 to 5, when you talk about discrete action spaces, let's say you can have only 5, right, or 5 or 6, 0, 1, 2, 3, 4, 5. But if you are using continuous action spaces, you can have an infinite option. And two key computations are centrally important for using and training stochastic policies. So one is sampling actions from the policy. So that's one of the important computation. And the second is computing log likelihoods of particular actions. So this is basically computing the log of this uh, you are having this policy pi, okay, so which is giving you an action conditioned on the state, right? So this entire thing is written as pi a condition to s. And in what follows, we described how to do these for both categorical and diagonal Gaussian policies. So categorical policy is like a classifier over discrete actions. You build a neural network for a categorical policy the same way you would for a classifier, and the input is the observation, which is followed by some number of layers, and then you have one final layer that gives you logits for each action, followed by a softmax layer to convert the logits into probabilities. And so what is sampling? Sampling is given the probabilities for each action. Frameworks like PyTorch and TensorFlow have built-in tools for sampling. So for example, see in the documentation of PyTorch, you have torch.multinomial or TF. In TensorFlow, we have TF.distributions. For these are I think for the Gaussian diagonal Gaussian policies, and for the categorical in TensorFlow you have TF.multinomial. So then if you have to compute if you have to compute the log likelihood, so denote the last layer of probabilities as p theta of s. So why is this p theta of s? This will give you the probability of the different actions, let's say in the last layer, uh, and the input that you are giving to this deep neural network is s, and it is a vector with however many entries as there are actions. So we can treat the actions as indices for the vector. The log likelihood for an action a can then be obtained by indexing into the vector. So that is how you get the log likelihood of the actions. And then we have so just like categorical policies, we have the diagonal Gaussian policies. And it's basically a continuous we can have a continuous set of actions in this kind of policy known as diagonal Gaussian policy. And it always has a neural network that maps from observations to mean actions. So what are mean actions? Mu theta of s, so where s is your input states. And there are two different ways that the covariance matrix is presented. So the first way is there is a single vector of log standard deviations, log of sigma, which is not a function of state. So the log sigma are standalone parameters. And the second way is, so there is a neural network that maps from states to log standard deviations, and it may optionally share some layers with the mean network. So what do we mean by sampling? Sampling is, so given a mean state action and standard deviation sigma, so mu theta of s and sigma theta of s, and a vector z of noise from the normal distribution, an action sample can be computed with. So if you are given a mean and a standard deviation of the policy, which basically gives you the continuous action space. So you would just say mu plus sigma into z, where z is the is a number from the normal distribution. So that is sampling. So you would get a particular value of this a. And so to compute the log likelihood of this action or this policy, you can say log of pi theta a such that s is equal to -1/2, and you can just use this formula. So what is a trajectory? A trajectory is a sequence of states and actions in the world. So for example, you are in a park, and you are at state S0. Now you take an action A0. Let's say you turn left, and now you are in another state S1. And now you take another action A1, that you walk for 5 steps. Now you will be in another state S2, and then you will take another action A2. So a sequence of states and actions in the world is known as a trajectory. And the very first state is randomly sampled from the start state distribution. So the S naught, it is denoted by rho naught. And state transitions which happen to be to the world between time t, so st at state t plus 1, which is st plus 1, to so st to t plus 1 is the transition from state, are governed by the natural laws of the environment. So we'll see how you would define an environment. So for every different problems, you will either have to define an environment of your own. For example, for our case, the environment will be let's say laws of physics, which are obeying the different laws of physics, and depend on only the most recent action A. So they can be either deterministic. So you can have either deterministic actions or you can have a stochastic actions. So actions come from agent according to its policy. And what are the rewards and returns? So reward function is critically important in reinforcement learning. It depends on the current state of the world, the action taken, and the next state of the world. So for example, ST is your current state, AT is your action. Now after taking the action, the environment will return another state, ST plus 1. So a combination of all these, the present state, the action, and the next state, that will tell us what is the kind of reward we are getting from doing from performing these steps. And although frequently this is simplified to just dependence on the current state or the state action pair, but it is actually a combination of these ST, AT, and ST plus 1. So the goal of the agent is to maximize some notion of cumulative reward over a trajectory. So what is the reward? A cumulative reward over trajectory, that is known as the return, right? So, but this actually can mean a few things. Will yeah. So that's about reward and return. So how would you mathematically represent the reinforcement learning problem? Whatever choice of return measure and whatever choice of policy, the goal in reinforcement learning is to select a policy which maximizes the expected return when the agent acts according to it. So you have to maximize the return by following whatever policy or whatever actions that the agent takes. And to talk about expected return, we first have to talk about probability distributions over trajectories. So let us suppose that both the environment transitions and the policy are stochastic. So in this case, the probability of a t-step trajectory, that will be basically the probability rho zero at S0. So that is the probability of the starting state, and which is you multiply. So you have this pi basically represents just like sigma, it represents a continuous multiplication of at t equal to 0, t equal to 1, and so on until t minus 1, capital T minus 1. So you have the probability of st plus 1 given st and at, and multiplied with this pi of at given st. So what will this pi of at given st give you? This is the policy, this is the probability of the action, and probability of the action given the state, and this is the probability of the state itself. So this is when you multiply both of these, you get a joint probability of the state action pair. And so the expected return denoted by j of pi is then, so j of pi you have to sum over all the so this is, so you follow some trajectory, s0, s0, a0, s1, a1, s2, a2. So corresponding to different state action pairs, you will get different taus or different trajectories. And so the expected return, which is denoted by j of pi, so it is a summation over all these taus, and it is the expected value of the return, given all the trajectories. So that is the expected return. If you average over all the trajectories, the summation of the rewards, that will give you the expected return. And the central optimization problem in reinforcement learning can then be expressed by, so you have to find out such a policy. Okay, so you can have this for a particular policy, right? For a particular state action pair series, let's say you go left, right, left, then walk 2 steps. These are different actions, so you can have different combination of these actions. So the problem is to basically maximize this return. Okay, and you have to find out the argument, so argmax. So you have to find such a policy pi which maximizes j of pi. So that is basically pi star. So pi star is the optimal policy, and that is the formulation of the reinforcement learning problem in a mathematical sense. Now there is a concept known as value functions, which are very important, and we'll come to. So these value functions are represented by q, and then there is something known as optimal q function, or which are represented by q. Sorry, value functions are represented by v, and these optimal q functions are represented by q. So value function, it's often useful to know the value of a state or state action pair. And by value we mean the expected return if you start in that state action pair and then act according to a particular policy forever afterwards. So, and value functions are used one way or the other in almost every RL algorithm. So there are 4 functions. So value function is only is there are 4 types. So you can have an on policy value function v of s. So you have to follow this policy pi. You start at a state s, and it gives the expected return if you start in the state s and always act according to the policy pi. So at every state following the state s, you just have to take the actions from the policy pi, right? What is pi giving you? Pi just takes the state as an input and it gives you the actions. Then we have the on policy action value function, which is known as the q pi, but it is a function of state action pair. So it gives you an expected return if you start in the state s, take an arbitrary action a, okay, which may not have come from the policy, and then forever after act according to the policy pi. So just at the starting, right, you choose the state s. You start from the state s, and then you take an action a, which might not be in accordance to the policy pi, but afterwards you follow the policy pi, and whatever reward whatever cumulative sum of average reward you will get following that trajectory, that is the on policy action value function. So then we have the optimal value function. So optimal value function is v star s, so which gives the expected return if you start in state s and always act according to the optimal policy in the environment. So if you remember, we have seen here what is the optimal policy. Optimal policy is pi star. So if you always go according to the optimal policy in the environment, that gives you the optimal value function. And then we have the optimal action value function, so which is q star of SA, so which gives the expected return if you start in the state S, take an arbitrary action A, and then forever act according to the optimal policy in the environment. So that is, so these are the fundamental concepts of value functions. And so you should know that when we talk about value functions, we do not make reference to the time dependence. We only mean expected infinite horizon discounted return. So value functions for finite horizon undiscounted return would need to accept time as an argument. And okay. So then what is the optimal Q function and the optimal action? So then there is an important connection between optimal action value function Q star of SA. So this is the optimal action value function Q star SA, and the action selected by the optimal policy. So by definition, Q star SA gives the expected return for starting in state S, taking an arbitrary action A, and then acting according to the optimal policy forever after. The optimal policy in S will select whichever action maximizes the expected return from starting in S. So after S, it will give you an action which will maximize the expected return until the last state. And as a result, if we have Q star, we can directly obtain the optimal action A star S via. So you can actually in an inverse manner obtain the optimal action from the optimal action val. So this optimal action value function. And so there may be multiple notations which maximize Q star SA, in which case all of them are optimal, and the optimal policy may randomly select any of them, but there is always an optimal policy which deterministically selects an action. Now there are these set of equations which are known as Bellman equations, which form the like it's at the core of reinforcement learning. And so all four of the value functions obey self-consistency equations called Bellman equations. The basic idea behind these equations is that the value of your starting point is the reward you expect to get from there, from being there, plus the value of wherever you land next. So wherever you are, what is the so the value of your starting point? It's basically the reward you expect to be, like you are in a particular state, right? Let's say you are at IITM, right? So you have to estimate, so what is the value of or what is the reward of you being in IITM. So the value of your starting point, so the starting point, let's say, is you are starting to study this course, climate data science, and the value of your starting point is the reward you expect to get from being there. So you are here, right? So you are learning, plus the value of wherever you land next. So after learning maybe modeling or programming, wherever you will go or whatever you will do next, whatever simulations you will do, you will so that is, so cumulative of that is the reward of your starting point, is the value of your starting point. And the Bellman equations for on policy value functions are, so you have value function v pi of S. So you start from a state S, follow a policy pi, and so the value function is the reward at this state. So you have a state action, so you take the action after this, plus gamma of v pi S prime. So S prime is, what is S prime? S prime is the next state which is sampled from the environment transition rules. So from the environment, after taking the action, you reach the state S prime, and And so the value of staying in a state S is the mean of, or the expected return expectation of the reward of being in this state S, such that you take an action A, and action A, which is also according to the policy pi, and plus gamma of V pi S prime. Similarly, for action value q of pi sa, that will be equal to similar to this the first equation. You have r of sa plus gamma of the expectation for the next state. So you can see that the Bellman equation is kind of a recursive equation, because expectation of the next state will in turn depend on gamma and the expectation of the state which is after the state S prime, let's say, which is maybe S prime prime. So the value, so you can also then write the Bellman equations for the optimal value functions. What are the optimal value functions? Where you will follow the optimal policy, right? So these are the Bellman equation for the optimal value functions. And the crucial difference between Bellman equations for on policy value functions and the optimal value functions is the absence or presence of the max over operation over actions. So you see here, you have to maximize over over actions. So you have to find out the actions which maximize your q, right? And its inclusion reflects the fact that whenever the agent gets to choose its action, in order to act optimally, it has to pick whichever action has the highest value. And the term Bellman backup comes up quite frequently in the reinforcement learning literature. So the Bellman backup for a state or state action pair is the right hand side of the Bellman equation, the reward plus the next value. So this right hand side term is known as the Bellman backup. And then we have something known as the advantage functions. So what are that? So sometimes in RL we don't need to describe how good an action is in absolute sense, but only how much better it is on average. So that is, we want to know the relative advantage of that action. So we make this concept precise with advantage function. So advantage function is a pi of which is a function of state action pair, and corresponding to a policy pi, it describes how much better it is to take a specific action in state S over randomly selecting an action according to pi. So in V pi S, you will randomly select an action, whereas in Q pi SA, you will at the starting state, uh, and following in the following states, you will follow the policy pi. So you have to say take q minus v, it will give you the advantage function. It is the value of the action relative to randomly taken action. So that's the main theory of reinforcement learning. So this was a short introduction on RL terminology, kinds of algorithms, and basic theory. So next is an essay on how to grow into a RL research role. So anyways, yeah, this one is generic. So then this is a taxonomy of the reinforcement learning algorithms. So it can be model free RL, or I think this will take some time. So what we will do now is we will do some examples from Keras examples. Maybe one or two we'll see, and we'll see reinforcement learning in the later classes. But those were the basics of until, if you know until Bellman equation, and you can understand what is q function, q of SA, optimal value function, and you can understand these four equations. You have a sound foundation in reinforcement learning. Okay, so then Yeah, we yeah. So these are Keras examples, and I'll try to cover all of them in this course as much as I can. So we will, let us see if we can. Okay. So let us see this example from graph neural networks. So it talks about node classification with graph neural networks, and so it's implementing a graph neural network model for predicting the topic of a paper given its citations. So many data sets. So this is the problem description, and it says that many data sets in various machine learning applications have structural relationships between their entities, which can be represented as graphs. So such applications include social and communication network analysis, traffic prediction, fraud detection, and so graph representation learning aims to build and train models for graph datasets. So this is the book that I think I've already shown in the class, the graph representation learning book. So you can go through this book as well, in addition to the to that blog from which we studied the graph machine learning. So it aims to build and train models for graph datasets to be used for a variety of machine learning tasks. And this example demonstrates a simple implementation of graph neural network model. The model is used for node prediction task on the Cora dataset. So what is this Cora dataset? We'll see that Cora dataset consists of 2708 scientific publications classified into one of the 7 classes. So there are 7 classes, and the each of these publication is classified into those classes. And the citation network consists of 5492 links, 5429 links. So that's the graph which is connecting all the different scientific publications, and each publication in the dataset is described by a 0 or 1 valued word vector indicating the presence or absence of the corresponding word from a dictionary. So the dictionary consists of 1433 unique words. So this is the Cora dataset, and okay. So there are different algorithms which are used for classification of this dataset, and this datasets the datasets are publicly available from MariaDB database. So open your favorite MariaDB client. Okay. Now we were seeing that, okay, so from this dataset we have to predict the subject of a paper given its words and citation network. Note that we implement graph convolution layer from scratch to provide better understanding of how they work. And however, so this is a implementation in TensorFlow from scratch. There are libraries such as Spectral, Stellar Graph, so and GraphNets which can do this directly for you. So let us first import these libraries, notably the NetworkX library for visualizing the graphs. And the Cora dataset, so again, consists of 2708 scientific papers, 7 classes, 5429 links, and each paper has a binary word vector of size 1433. So you first download the dataset Cora. There are 2 tab separated files, Cora.sites and Cora.content. So Cora.sites include citation records within 2 columns, cited paper ID, which is the target, and cited paper ID, which is the source. And Cora content includes the paper content records with 1435 columns. So paper ID, subject, and 1433 binary features. So these are the contents of the Cora content and Cora sites. So you can download it using Keras utility. So they have included this function in Keras as well now. And so this is the data directory. And so you can read this as a pandas data frame. So Quora dot cities, and what are the name of the uh, target and the source. Yeah. So which has so this Quora dot sites, this has got this is a pandas data frame with 2 columns and 5429 rows. So you can see that we can display the sample of citations data frame. So the target column here, so this is the ID of the paper which is target, and this is the source. So this paper is citing this paper, and these are the different rows in that data set. So now let us load the papers into a pandas data frame. So you can see that they are now loading this Quora.content table or data frame. So this has got 1435 columns. So the first column is paper ID, then it says the second is paper subject, and 1433 binary columns. And then this consists of 2708 rows. So now we display a sample of the papers data frame. So this is a sample of the papers data frame, and it consists of so this is the paper ID. So these are the paper IDs. The data frame includes paper ID and the subject columns. So there is a column, yeah. So this is the paper ID, and we have the subject column here. And so they have sampled like five rows from this data set. So these are the subject is rule learning neural networks probabilistic. So these are the five subjects here, and these are the paper IDs that are being extracted, that are being sampled here. And so just displaying the value count here, we can see. So for the subject, so there are these 1 2 3 4 5 6 6 7. So there are basically just 7 subjects, and value count is giving the number of rows which have these particular subjects, right? And we convert the paper IDs and subjects into zero based indices. So you can see this class values. So these are for the subject. So you sort the papers by unique, and so the class IDX and the paper IDX you extract using this syntax. And then you make another data frame, so which consists of, so paper ID equal to, so you apply this paper ID into this data frame, and the citations which has got the new columns, the new rows, source and target, and the paper subject. So then using the network X library, so nx.draw spring, you can see the visualization of this citation network. So this is the visualization of the citation network. You can see that there is a central graph, and then there are these different people who are, or papers who are citing each other. But then here there is a lot of citation that is happening. So split the data set into stratified, train and test sets. So for the training, so the train data shape, that is 1360, test data is 1345. So you can see 1435 columns here, and implement train and evaluation experiment. So these are the number of hidden units: 32, 32, learning rate as 0.01, 50% dropout rate, 300 epochs, and batch size of 256. So now to run the experiment, we'll have model.compile optimizer equal to, so you take this optimizer as keras dot Adam optimizer sparse categorical clause entropy as the loss function, and sparse categorical accuracy as the metrics, which you are just computing, but the optimization is only being performed on the sparse categorical cross entropy. So we are also using early stopping as a callback, and so we will fit the model here. So this one takes in as an input the model. So we'll see the how to define the model. So model dot fit x equal to x train, y equal to y train. So these are the epochs, batch size, validation split, and so this is displaying the learning curve for the validation loss and the for the validation accuracy, for the train loss and train accuracy as well. And here we will create the feed forward network. So you can see we have taken as an input the hidden units, the dropout rate. So initially these are the, so we create a list fnn layers, and then to fnn layers we keep appending we keep appending layers dot batch normalization, layers dot dropout, and layers dot dense. So starting with batch normalization, dropout, and then dense, you do that for as many number of hidden units are there, right? So then you return keras dot sequential fnn layers name equal to name. So name also you can define for this create feed forward network, and then we will see the creation of a baseline neural network model. So this is the baseline model. Yeah. So where your inputs, you have the shape as number of features, and you give this as an name as input features, and then you use this create ffn function, which basically generates. So if you remember, we had defined the hidden units much before, so which was 32 comma 32. Yeah. So here we had defined the hidden units as 32 comma 32. So this will loop over the hidden units, and this will generate this feed forward network. So then you pass this input to this feed forward network, that will give you an x, and then you so for block idx in range 4, so you 4 times you loop over here, and then you create this ffn block, which has got this name according to the block idx, and you also add this skip connection. So this is like you connect the x and x1, so this becomes the skip connection. Do this 4 times, and then you have this logic. So the number of classes, the n number of classes that you have, so for that we use the dense layer from the layers class, and you return keras dot models. The input is inputs, and the output equal to logits, and you call this as baseline. So baseline model equal to create baseline model, hidden units, number of classes, dropout rate, and the baseline model dot summary. So you can see this. This is the baseline model that we have, and so for training the baseline classifier, we will use this function that we created, run experiment, which just takes the model x train y train, and it trains the classifier. So this is the model, this is the x train, this is the y train. So our model is training here now, and you can display the loss functions or the curves, and the accuracy for the training and the testing data. So you can see that the test error is started to increase slightly. So somewhere here is the optimum model that we have, and we can compute the test accuracy, which is coming to somewhere around 73.52%. And then you can do, yeah, different things with this. And yeah, so now you can start building your graph neural network. So yeah, you can see this at your end. Run this in Colab after the class, and we can try to cover this in the following sessions. So yeah, with that, I would like to end the class for today. And if there are any questions, then please feel free to uh, ask now.